So in last class, we started the insertion sort. We have shown the algorithms. You know already the insertion sort. The element is pushed at the last and then inserted at the last of the array, and then we check its proper position and we shift the elements, and we keep a make a positions for the new element at the proper positions where it is to be placed, and the other elements are shifted. It's like, you know, the algorithm. So this is the algorithm, and we are assuming the cost of each statement is c1, c2, c3, like that, and the time required depends how many times, means how many times this statement is executed. Okay, how many times this first line is executed, n times, then n minus 1 times for the next statement, like this. In this way, uh, the times means actually this is number of times they are being executed. Okay, how many times. So in this way we now find the total cost of the algorithm. How? That we multiply c1 with n, then c2 with n minus 1, then 0 with n minus 1, like this. 0 means the comment is not being executed, that's why its cost is 0. So in this way you find out the cost of each statement and how many times each statement is being executed, and then multiply them and find the sum of them. That will be the total running time complexity. This is the TN, running time complexity of the problems. Now here you see this entire expression, this entire expression is a function of n. Okay, just like a function of n. Now best case means when occurs when the number are already ordered. So this is the Tn in that case, but you check also it is a function of n, k1n into k2n, where k1 and k2 are two different constants whose values are given by this. Similarly, the worst case also we have shown in the last class, that when the elements are in reverse order, then you have to best case in insertion sort of occurs when suppose the list is already sorted. When the list is already sorted means these are the elements, suppose 2, 4, 6, 8, 10, like this. So if you are inserting means considering that, okay, this is sorted, now if you are placing it at the end of it, then we know that these elements are all less than this, so no element will be shifted. So this is the best case, and worst case occurs when the numbers in reverse order, means just in reverse order, then you have to shift all the elements, and in that case the Tn will be the quadratic. Quadratic means, you see, 2 highest power is this, so this is the function n square, means if you simplify it you will get like a this, and we have used a stands for c5 plus c6 plus c7 by 2, like this. These are the constants, a b c. So now basically we see what the running time complexity Tn is a function of n, is a function of n. Okay, so that's why I think you have means you already have read this big O notation in Nanda Dulal Jana sir class, because he took the functions chapters and at that time he has told. Okay, so again we will repeat that, but you will get so many examples also. So how can we measure the time complexity of a program, or how can we compare? So there are some uh, tools. The tools means in that case there are how to measure. So there are some notation. So this is called big O notation. Okay, big O notation. This is the big O notation. Big O. Don't write in exam small o. Small is O is different. Okay, so whenever you will write O, then you should make it larger so that everybody understands that this is the big O. So big O notation gives what, the upper bound on the running time. Upper bound means it will take at least means not more than this, means upper bound. Okay, any program has upper bound and lower bound. Means if a program you are executing a program, then you will say it will take at least these many steps. That is called lower bound. Upper bound means, oh, whatever be the case, it will not take more than this. That is called upper bound. So big O notation is used to provide upper bound of the running time of any program. So So what is the mathematical definition? Mathematical definition is that a function fn is said to be of big O of Gn. Okay, never say equal to. Please remember, although we are using this symbol equal to, but you should not say that fn is equal to big O of Gn. Then it is wrong. Then it is wrong. I am coming it later. You should say that fn is. Okay, you should say fn is, or you can write also like this: fn belongs to big O of Gn. That is also correct. But never say is equal to. Why? The reason is that the right hand side, this is a set. Okay, first you see the definition. What is the fn? Fn is said to big O of Gn if there exists two positive constant. Two positive constant. What are the positive constants? C and n naught. Such that for all values of n, for all values of n equal to n naught, we have fn is less than equal to c into gn. Then we call that function fn is big O of gn. Now come here in this figure. See what happens. In this case, this blue curve is fn. This is fn. Okay, and this is, suppose if we multiply fn by a constant, I am getting another curve like this. And here you check b intersecting here, also intersecting here. Okay, they may intersect so many times, but you see after this point, means after this n node, n equal to n node, n equal to n node. So up beyond this, fn is always less than equal to c into gn. Why? Because you see this is the value of fn here. Check it. This is the fn. And what is the gn? This portion is the gn here. C gn. So here you check that fn value is less than c into gn always. Just after n node, beyond n node, you check whatever be the values of n. If n is greater than equal to n node, fn is always less than equal to c into gn. So in this case, we will say that fn does not increase more than the c multiplied by a gn multiplied by a positive constant c. So that means fn is being upper bounded by gn. Okay. So fn is said to be of order of gn. This is the mathematical definition, and this is the graph. Okay. So here this graph also implies that fn grows no faster than some constant times c into gn. Some constant times gn means c into gn. Clear? So that's why it is called upper bound. Now, why we should not say fn is big O of gn? The reason is that, okay, can you give me an example of big O of say n? What are the example of big O of n? Say fn
Sir,
equal
any
to,
polynomial with n as the degree, like
yes,
of any linear
2n
polynomial,
plus, yes,
2n plus 1.
2n plus 5, or say suppose if fn is 3n plus 2. Clear? So these are all big O of n. Big O of n. Clear? So what do you mean by big O of n? Big O of n means S. This is basically a set, because this is also big O of n. This is also big O of n. Yes, there are so many functions that can be big O of n. So all these functions, for example, just a minute. Uh, Here you see, I am sorry. Say this. This is the big O of n, where 2n plus 5 is there, 3n plus 6 is there, or say n plus log n plus 2. Here you see I will say why it is big O of n, because log n grows slowly, then then n. Okay, you know the curve, because the curve you check, this will be the n curve. But log n curve will be like this. Okay, so automatically log n is larger. So in this case, this a 2n plus log n plus 2, this will be big O of n. Similarly, there will be so many other functions that we are not writing. It can be say 3 by 2 n plus 6, just like this. So there may be so many functions. So this big O of n is what? Basically a set. Is it clear? These are all set. These are the elements of set. Now, can you write that 2n plus 5 is equal to this set? Can you write? Tell me. There is a set. There are so many elements. Now, can you write if an element A occurs that A is equal to S? Can you write? Tell me.
No, sir.
No.
No, sir.
An element, because the left hand side is an element and right hand side is a set. Set is a set of element, collection of elements. So element cannot be equal to this. So that's why here also you cannot write, you cannot say that 2n plus 5 is equal to, you cannot say is equal to. No, you should not say. You should read that 2n plus 5 belongs to big O of n or 2n plus 5 is n. But don't say is equal to. Although we are writing like this, but don't say like this. So in some books also you can see that like this big O of n, big O of n. Is it clear now?
Yes, sir. Yes, sir.
So although you are writing like this, but don't say like is equal to. Now this is one definition. Another definition is that, what is the another definition? Another definition is says that if there is a limiting definition, if limit n tends to infinite, fn by gn exists. If this limiting value exists and fn by gn is not equal to infinite, then we'll say fn is big O of gn. Then we'll say fn by gn means if this is not equal to infinite, then we will say fn is big O of gn. See here, fn is 2n cube plus 5n plus 7. Another important characteristic, don't think it is only the mathematical, but here you see that n tends to infinite, or for here you check n greater than equal to n naught. What does the physical meaning of this? 2n is greater than equal to n naught. The physical meaning means, I am saying in algorithmic sense, see, you are writing a code for solving a particular problem, or you will say that whatever be the number of elements, these will give that this much time complexity. Now here see, whatever be the number of elements means n may be very very large. It is not that n is less than 100. N can be anything. Okay, minimum at least suppose there should be say 5 elements for example, but it can have any element, any number of elements. That's why n is greater than equal to n naught. You check for all values of n greater than equal to n naught. Its meaning is that n can be, means basically n is less than infinite. Okay, you can take very large value of n, but it is also always greater than equal to n naught, because no element cannot be equal to infinity, because you know that if you say a number is infinite, then I will add another element plus 1 with that to get another larger number. Larger, so that will be the infinite. So infinite is not, means undefined. Okay, but you see n can be very large. N can be very very large. So that's why n is greater than equal to n naught. Means in your case you can sort huge number of elements. There should not be any foundation that your program cannot handle more than 1,000 elements. No, your algorithm should not be like that. So in that sense, this is the mapping of theory and the your algorithmic definition. Now, fn is an example. Fn is 2n cube plus 5n plus 7. Now, can I write this? This I can write like this as the less than equal to 2n cube plus 5n cube plus 7n cube. So that means this is 2 plus 5 plus 7, 14, 14 n cube. So here you see that this expression is less than equal to 14 n cube for all values of n greater than equal to 1. Clear? So here this is C and this is the value of n naught. Now your friend may say that okay, instead of 2n cube plus 5n plus 7, we can write like this, that this expression is less than equal to 3n cube. But if he writes 3n less than 3n cube, then what does it mean? If I shift all these terms to the right side of 3n cube, so what does we will get that n cube minus 5n minus 7 should be greater than equal to 0. And here you will get some values of n for some values of you can middle term factor, you can factorize it, or then you can find out for what values of n this is greater than equal to. You may get some larger than 1, obviously, because if n is 1 then it cannot be positive. If n equal to 2, you see 8 it's not possible. 3 for example, this is true, greater than equal to 3. So your friend also says that this expression is uh, less than equal to 3 into n cube, where n is greater than equal to 3, and you are saying this is less than equal to 14 n cube, where n is greater than equal to for all values of n greater than equal to 1, and here you are saying for all values of n greater than equal to 3. So both are correct, both of them are correct, because both are then saying that this function is big O of n cube. So that means if you choose some different c, then you will get different n naught. So answer should be same, big O of n cube. But if anybody says takes different c, then he or she will get different n naught. Similarly, here also you see what is Fn. Fn is this. So limiting definition, Fn by Gn, if it exists and Fn by Gn does not equal to infinite. So here you check what is Fn by limit f sorry n tends to infinite, Fn by Gn. Gn is this n cube. So if you divide it, what will you get? You will get, tell me, 2 plus 5 by n square plus 7 by n cube. I am dividing Fn. Fn is this by Gn. Gn is n cube. So if I divide this, what will be the answer for this?
Sir, sir, this one only, sir. The one you've written.
The answer is limiting value is
Mm,
n tends to
two.
infinite. 2,
Yes,
right?
sir.
Only 2.
Two, two.
Two,
Only
two.
2. So you see this definition that is not equal to infinite. It exists, yes. So the Fn is big O of Gn. So big O of Gn, what is Gn? Gn was n cube. Actually, here I have not written the middle step, that Fn is 2n cube plus 5n plus 7, and Gn was n cube. Okay, so that means this. So this is the definition of big O of n, big O of Gn. So another case, you instead of writing Fn is, suppose you have given an expression. Now I don't bother about the lower terms. So what? How can I write? I can write this expression as just like 2n plus mu q plus big O of n square. This portion I am writing big O of n square, because we are not interested about the lower end, lower order terms. Okay. So I need only these terms. So that's why I am writing like this. You can write, but actually this function is big O of n cube, fine. But suppose instead of you you have to compare this function with other functions, so you are writing like this. In that case, I need only the larger terms, and the other terms I can ignore. Ignore means we are not interested, so that's why I am writing this is the big O of n square. Next, this is the Okay, just before starting big omega of this, I should say another things. Uh, Here you see, say
Sir, could you go to the previous slide just once, sir? Sir, I couldn't read one thing, sir. Sir, sir, the second example, sir, I didn't really get it, sir. Why would I write 2n cube plus O of n square? Like, are we only
this portion is big of n square or not? You tell me.
Yeah, yes, sir, yes, sir.
So suppose you are not interested to write the every all the details 8n square plus 5n plus 7 log n plus 8 something.
Okay, okay,
Instead of writing that, we can write. This
okay,
is the we can write. I am saying.
okay, okay, sir.
Now, suppose you have written an example. Say fn is 2n square plus say 2n plus 1. This is it. Now you are saying what is the time complexity? Sorry, what is the big this fn is big of what?
N
Tell me.
square.
N square. Now suppose your friend is saying that this fn same. This is big O of n cube. Now my question is he correct or not?
Sir, he is correct, sir, but it's loosely bound.
See, yeah. So he is also correct. Means he also can show that this expression 2n square plus 2n plus 1 is less than equal to some constant into n cube for all values of n greater than equal to say different n naught. Yes, he is also correct. But we will take this because we are considering the upper bound. Upper bound means what? That fn is not greater than this. Clear? So, for example, if I ask, suppose you are Mr. A, I am asking Mr. A that what is your height? What is your height? Clear? Mr. A. So, now he is not saying the height of his, he is not saying his height, but what he is saying, suppose that another B and C are there. Now he is saying me that height, my height is less than the height of B. Or suppose he is saying also that my height is less than the height of C. I know the height of B and C. Suppose he is, for example, he is 5 feet and he is say 7 feet. And he is saying that his height is less than the height of B, or he is saying another statement that his height is less than that of C. So which will be better to guess the height of him?
It is less than B.
Less than B. Fine. So that means because actually he is saying in terms of upper bound, it is not more than that. So I should consider that case where he is saying that his height is less than this and that height is minimum among all other cases. In this case, the two cases. So here you see both are correct. Big of n square, big of n cube is correct for this function fn. Fn is big of n square and fn is big of n cube. But we will take big of n square because this is big O notation is used for upper bound, and upper bound should be as low as possible. Okay, it should minimize. So I should take that n square. Is it clear now?
Yes, sir.
Now, next, big omega. What is the big omega? Big omega is provides a lower bound. Okay, it gives the lower bound with constant factor of the running time. Now, what is the mathematical definition? A function fn is said to be of big omega of gn. Okay, in this case again I am saying the same thing. Don't read it as equal to. No, don't read. So you should read it as just only is, or you should give the belongs sign. Fn is big omega of gn if there exists two positive constant c and n naught such that for all values of n greater than equal to n naught, fn is greater than equal to c into gn. This is the one definition. Exactly same with the previous one, except difference is this. Clear? In that case, it was less than equal to. Here, it is greater than equal to. Now, definition 2 says, so here the first, before starting the definition 2, you see this is the example. This is the Fn. This is the Fn. Okay. And this is the C multiplied by Gn. And after these, you see, check this at any position you take Fn, and this is Fn, and this portion is Fn, and this portion is C into Gn. So Fn is always greater than equal to C into Gn beyond this point. Clear? N not. So here you see another definition. If limit n tends to infinite, Fn by Gn exists, and Fn by Gn is not equal to 0. Here not equal to 0. Then we will say Fn is big omega of Gn. So here actually informally this definition says that F grows at least as fast as some constant time G. Okay. At least as fast as constant time of G. Example here. So Fn is 2n cube. So here you also you can prove that this is greater than equal to some constant into n cube. For example, C is 1 for all values of n greater than equal to n naught. You choose. So I am not writing the what will be the value of C and n naught. You can choose yourself. First choose C, then you will choose n naught. So it is not mandatory that all the students will choose the same C. They can choose different C. And please remember, this is very important. Big omega notation is very important. Don't think that big omega notation is very important only. Big omega is also very important. Why? You will see that when we will discuss the lower bound for sorting algorithm or for different algorithm, convex algorithm, what happens in algorithmic study, it is a really challenge to reduce the time complexity of an existing problem. Suppose there exists a problem and there exists a solution for also it. Now, will you not try to improve? Yes, you must try if it is possible to reduce the time complexity. So, for example, big O of n square, sorting time. You know already big O of n square. For example, bubble sort takes big O of n square. Okay, big O of n square time. Now, it was a challenge. Is it possible to reduce the time complexity from big O of n square to say n log n? Yes, it was possible, and it was designed by Sidgwick, the quick sort algorithm. You know, okay, or say merge sort. Better merge sort always it will take big O of n log n time. So now next question arises: is it possible to find out that the solution I mean sorting in linear time instead of n log n means further reduce? But means you should try. But if but in this case I am saying if you try to sort, then you will be failure, because in case of comparison by sorting, it is not possible to find out linear time sorting. Means you should compare. If you compare the elements and you want to sort, then it is not possible. Means n log n is actually the lower bound. Nobody can reduce the time complexity below n log n if he use the sorting based on comparison. It's not possible. So that means you have to show it, prove it by mathematically. Why it is not possible. So that's why big O notation is very important. Big omega. Because if you know that the sorting needs big omega of n log n time, then you should not try to reduce it, because that will be the wastage of time. Why you should waste your time unnecessarily? So that's why you should know what will be the lower bound for each problem. So there exists so many problems for which we do not know still, do not know what will be the lower bound. Is it possible to reduce further or not? We do not know. So that is also a challenge. Now theta notation. What is the theta notation? The theta notation provides the asymptotic tight bound on the running time. A function is here, it is tight. Tight means both upper and lower bound. Okay, tight means upper and lower, and they are same. So same means the same function. Here you see a function is fn is said to be of theta of gn, and it is written as fn is theta of gn if there exists three positive constants c1, c2, and n naught, such that for all values of n greater than equal to n naught, we have this c1 fn is greater than equal to c1 into gn and less than equal to c2 into gn. You see the both the functions here is gn and this gn, they are same, they should be same, otherwise it is not theta of gn. So fn is greater than equal to c1 gn and f2 is c2 into gn. So in other words, we can say this as what? Fn is big O of gn and fn is big omega of gn. If both these and these are correct, then we can say fn is big O of b theta of gn. So alternatively, we can write if fn this is the limiting definition, it exists, and this is equal to k, where k is greater than 0 and less than infinity, then we will say this is theta of gn. So I have already said, okay, this fn is theta of gn if and only if fn is big of gn and fn is big omega of gn. Here you can show that 2n plus 5n n cube plus 5n plus c, this is less than equal to 14 n cube and greater than equal to just n cube, and you can it is true for n greater than equal to 1. Okay. This is uh, this is less than equal to 14 n cube, and this is greater than equal to n cube for all values of n greater than equal to. So this is theta of n cube. And what is small o? Small o is also almost same as big O. Only one definition difference is there. You see, a function fn is said to be of order of small o of gn. Just you write like this. Don't say is equal to. If for every constant c greater than 0, there exists a positive integer n naught such that for all this is fn is less than c into gn. Please check it, not greater less than equal to. Okay. And here you also see if for every constant, for there exists a constant, if for every constant, these are the two different difference from big O. For every constant c greater than 0, there exists a positive integer n naught such that for all this is less than only. And in this case, if it will be 0. That was not equal to 0. Okay. Fn by gn and fn by gn is equal to 0, we shall say fn is big. So example, here you see this 2n cube plus 5n plus 7. This is, you should find out that less than, and you take the larger term than this. What is the largest time? 3. So you can take 3.3.1. Okay. And for you can take any c, and for all values of n greater than equal to some n naught. Always please remember that if it is 3, so you can write it is small o of 3.1. Now somebody can write also like this. This is small o of n to the power 3.01. Yes, he is also correct. No problem. You are writing that this. But you see fn is not less than equal to big O, small o of n cube. Here also you see the definition, second definition, that fn by gn should be equal to 0. So what is fn? To this fn is Okay, you know already. Fn is written here, and gn. What is gn in this case? Here. So you, if you divide fn by gn, so what happens? That limit n tends to infinite, and if you divide it by, so it will be like that, 2 by say n to the power 0.1 plus 5 by n to the power 2.1 plus 7 by n to the power 3.1. Okay. So in this case, if you put n tends to infinite, so what will be the value? Tell me. What will be the value? Here?
Zero. Zero.
0. 0. But if you take g as n cube, then what happens? Fn by gn, that becomes 2 plus 5 by n square plus 7 by n cube. And if you take the limit of it, so limit of it, so it will be 2, not equal to 0, but it should be 0. Clear? So this is small o of gn. Now you may ask me, sir, what is the use of small o? Yes, there is a use of small o, although it is little of little use. You see what happens. So suppose for some problem, for some problem, uh, you have reduced. Suppose there is a problem P. There is a problem P. Okay, and there exists a solution for this, and it takes big O of n log n time. Clear? Now, what is your objective? You will reduce the time complexity. Now, what is the means? If you try to reduce the time complexity, your objective is to big O of n. It will be better. But suppose this becomes very hard. Very hard means you cannot design. It's really hard. But you have find out a solution. You have find out a solution whose time complexity time is smaller than big O of n log n, but not equal to big O of n. Clear? Your time complexity, you have find out a solution. Clear? That solution is less than big O of n log n, less than big O of n log n, but not big O of n. So that means actually you will say that your solution is small o of n log n. Means it is less than n log n, but not equal to n log n. It will take small o, it is small o of n log n. Clear? Small o notation is used to denote that you have find out a solution which is smaller than that the argument that lies inside the parenthesis. You probably have not reached the means well-known parameters, means I mean say linear or like that. So it may happen that suppose another example, that you have a problem and you have a solution big O of n square, and you are trying to reduce it. You are trying to reduce it, but you cannot get. You are not getting big O of n log n. You are not getting big O of n log n. But this is means suppose you have obtained big O of n square root of n. Now you can write, instead of big O of n square root of n, you can write this is small o of n square. Clear? Because we human being generally prefer n square n log n like this. Whenever you will say n square root of n, we sometimes we are not habituated with this complex time complexity. So sometimes you people may write small o of this. Similarly, another definition is there
Sir, but
also.
won't that be loosely bound, sir?
Yeah.
Sir, but won't that be loosely bound, sir, instead of tightly bound? If, like, for example, if in case of n root n, I write O n square directly, won't that be loosely bound?
No, no, you are saying that it is less than. Suppose you could not compute. I am saying you could not compute the exact value of it. But you know, you are showing that it is less than n square. Whatever a complex expression is there, that is, you are saying that this is less than some constant into n square. Always.
Okay,
Okay.
okay, 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 sir.
It is small o of n square.
Okay.
Now small omega is also there. I have not means I have never seen the application of it. It is of very little use, I think. Okay, but technically you should know what is small omega. Just the opposite definition: c greater than zero. If a function fn is said to be of big omega of g, sorry, small omega of gn. Okay, if for any constant c greater than zero, there exists a positive integer n naught such that for all values of n greater than equal to n naught, if n is greater than c into gn, it is not equal to, check it. This is the definition, a difference. This is the difference here and here for any constant, and here it will be zero. This here same thing. If n is 2 n cube plus c, so we can say that this is small omega of n square, but we cannot say it is small omega of n cube. It should be larger than this. Okay, this larger, this value, and check. There should be a difference. This should be larger than this. Now, what are the properties of this? Fn is uh, big omega, big O of Gn, and Gn is big O of Hn. So Fn is big O of Gn and Gn is big O of Hn. So that means what? Big O, Fn is big O of Hn. Can you prove this? Okay, in next class I will discuss this because time is. Thank you for attending.